Hello again. We're going to go over a topic called separation by precipitation, otherwise known as selective precipitation, making use of the difference in solubility of some sparingly soluble salts to try and separate those salts. So in this particular case, we have some soluble form of calcium ion and of strontium ion, and we're going to precipitate them as the carbonates by adding the soluble sodium carbonate. So first we need to figure what's going to precipitate first, and since CaCO3, SrCO3, both of those are 1-to-1, so all we have to do is compare the KSP values, and strontium carbonate at something times 10 to the minus 10, it's about 10-fold less soluble than calcium carbonate as aragonite. So strontium carbonate will precipitate first. So first of all, we decide, and this is totally your choice, totally arbitrary. Well, first we'll say strontium ion as the carbonate is going to precipitate first. And we want to precipitate 90% of it before the calcium carbonate begins to precipitate. So we want to leave 10% behind. So that equals 0.1, 10%, times, what do we have, 0.035. So that equals 3.5 times 10 to the minus 3 molar left. All right. Now, at that level of strontium left in solution in this system, what we want to know is what is the carbonate concentration going to be. And so this is a KSP problem with a common ion. So we say KSP equals, that's strontium times carbonate concentrations, and that's going to be, so we plug in our KSP. So KSP and that's going to be equal to the strontium we have left, the common ion. I said carbonate, but that's not correct actually. Right now we've got 3.5 times 10 to the minus 3 molar, and our unknown in this case is the carbonate ion concentration. So carbonate ion concentration is going to be equal to 5.6 times 10 to the minus 10 divided by the strontium concentration, 3.5 times 10 to the minus 3. And so that equals, that is 1.6 times 10 to the minus 7. All right. Now we take that And is that going to let me get some things out of the way here of my view. So this is what we call Q, the reaction quotient idea. So we plug in what we've got. We say Q is equal to, once again, it'll be, we want to wonder now about calcium times carbonate. Oops, that's 2 minus. And our calcium concentration is 0.03 molar. And we just figured out our carbonate concentration, 1.6 times 10 to the minus 7 molar. And that equals 4.8 times 10 to the minus 9. Now, let's compare that to the K, and the K value is 6.0. So we say Q 4.8 times 10 to the minus 9 is less than, only slightly less than actually, is a little bit less than the, what is it, 6.0 times 10 to the minus 9. So this is Q is less than K. That means the reaction will proceed to the right. That is, it will not precipitate. So that separation technically should work. In practice, I doubt that it really would, with the other KSPs being that close to each other. I'm going to say will work, question mark. In any case, that's the idea. You take this, once again, let's recap. Make your decision about what is a good enough separation. That's your choice. It's arbitrary. So 0.1 is left. We want to drop out 90%. And then that times our initial concentration gives us what we hope to have. So at that strontium concentration, we use the common ion effect to calculate the carbonate concentration at that time. And then we calculate the reaction quotient Q, given our initial calcium, which should still be in solution, and our carbonate, which we have just calculated up here, and then compare that Q value to the KSP for the calcium carbonate. And so technically that is less, but not by a lot. So the separation may or may not work, but technically it's perhaps worth a try. So that's all I have for now.